Hello everyone, I'm Dr. NAVNEET KAUR, Associate Professor in Department of Electronics and Communication Engineering, Sagar Institute of Research and Technology College, Bhopal. Today I'll be taking my 9th lecture on subject Digital Signal Processing. In today's lecture I'll be discussing on the topic Discrete Fourier Transform. Now, first, we will see what is discrete time Fourier transform, which is written as DTFT. Now, suppose if we have any discrete time signal in time domain, and we want to find out its frequency representation, then in that case, the tool which is used is discrete time Fourier transform, which is DTFT. So the Fourier transform of aperiodic finite energy discrete time signal is called discrete time Fourier transform DTFT. That means the signal which is being transformed into frequency domain is aperiodic and it is discrete in nature. Now mathematically DTFT is represented as x omega, which is given by the formula summation n is equal to minus infinity to infinity xn e to the power minus j omega n, where xn is the time domain representation of signal and x omega is the Fourier transform. Now, if I want to find out inverse DTFT, that means if I want to find out xn from x omega, then xn is given by the formula 1 upon 2 pi integration over the time interval, which is fundamental period, minus pi to pi x omega e to the power j omega d omega. Now, the main characteristics of DTFT, it is that it is periodic in nature. The frequency range of omega is from minus pi to plus pi or from 0 to pi. That means x omega is periodic with fundamental period 2 pi. Now we will prove this. Now x omega is given by the expression summation xn e to the power minus j omega n, where n is from minus infinity to plus infinity. Now if I prove that x omega plus 2 pi k is equal to x omega, in that case it is obvious that x omega is periodic with period 2 pi, where k is any integer. Now, in this expression, I'll put omega as omega plus 2 pi k. So in this formula, wherever omega is there, I will write omega plus 2 pi k. Now, after substituting here, I'll get the expression on right hand side here. Now, using the property of exponential, I will break this into two terms. So it will be e to the power minus j omega n into e to the power minus j 2 pi k n. Now, according to Euler's formula, e to the power minus jx is written as cos x minus j sin x. So, e to the power minus j 2 pi kn will be written as cos 2 pi kn minus j sin 2 pi kn. Here, cos 2 pi kn is 1, whereas sin 2 pi kn is 0. So, this e to the power minus j 2 pi kn will be equal to 1. That means this term will become 1 and we will be left with the remaining term. So x omega plus 2 pi k will be written as summation n is equal to minus infinity to infinity xn e to the power minus j omega n, which is equal to x omega. So here we have proved that x omega is equal to x omega plus 2 pi k. That means DTFT is periodic with period 2 pi. Now, condition for existence of DTFT. We know that Fourier transform is convergent if summation of n is equal to minus infinity to infinity, absolute value of xn is less than infinity. That means Fourier transform exists only if discrete time signal is absolutely summable, and it is the necessary and sufficient condition for the existence of the Fourier transform. Now, we will see the example of finding DTFT. Now, we want to find out DTFT of unit impulse function delta n. Now, using the formula of DTFT, which is this. Here I'll put xn as delta n. So delta n is equal to e to the power minus j omega n. We know delta n exists only at n is equal to 0. That means it is equal to 1 when n is equal to 0, and it is equal to 0 when n is not equal to 0. So putting here, we will see that of all the values from n is equal to minus infinity to infinity, I will take only n at 0, because here only delta n is 1, otherwise it is 0. Now I'll take 1 into e to the power minus j omega n at n is equal to 0. So e to the power minus j omega 0 will be 1. So we have seen that the Fourier transform is 1. So delta n is having DTFT as 1. Now in another example, I will find out Fourier transform of exponential pulse a to the power n un, where magnitude of a is less than 1. Now using the formula of DTFT, now I'll put xn here, which is a to the power n un. So substituting a to the power n un, now we know un is defined at only positive values of n and at 0. That means at n less than 0, un is equal to 0. So instead of writing summation from n is equal to minus infinity to infinity, I'll write it as 0 to infinity. So, and in this range, un is having value 1. So it will be written as a to the power n. Un will not be written because it is having value 1, and e to the power minus j omega n. Now combining these two terms, ae minus j omega raised to power n, where summation n is equal to 0 to infinity. Now, if I solve this summation from n is equal to 0 to infinity, I'll see that this is the finite G. This is infinite GP, because here n is from 0 to infinity. If I'll put n 0, I'll get 1. Then if I'll put n 1, I'll get ae minus j omega n, n2 ae minus j omega squared till infinity. Now, we know that the sum of infinite GP is given by a upon 1 minus r, where a is, I'll show you with the formula. Thus, infinite GP is written as a upon 1 minus r, where a is the first term and r is the common ratio. First term we have seen, which is obtained when I'll put n is equal to 0. So first term will be obtained at n is equal to 0, which is 1. And common ratio is ae minus j omega. So here in the formula, a as 1, 1 minus common ratio, ae minus j omega. So this will be the Fourier transform. Now providing this common ratio should be equal to, should be less than 1. That means the magnitude of this common ratio should be less than 1. Now we can see that this common ratio is having magnitude A, and I have already mentioned that magnitude of A is less than 1. That means the condition for infinite GP is satisfied. So this will be the Fourier transform of a to the power n un. Now, next we will do discrete Fourier transform, which is written as DFT. Now, DTFT, which we have already seen, that it is continuous in nature and it is also periodic with period 2 pi. Now, since DTFT is continuous in nature, it is not appropriate for analysis in discrete signal processors. For converting it into discrete domain, we will sample one period of DTFT. Whenever the sequence is periodic, we always analyze it for one period, because the same analysis will be done for other intervals. So DFT is a finite duration sequence which is obtained by sampling one period of DTFT. Now we know that DTFT is periodic with period 0 to 2 pi. So sampling will be done at n equally spaced points over the period. So interval between the two samples will be 2 pi by n. So DFT is obtained from DTFT by putting value of omega as 2 pi k upon n, where k is integer. K can be 0. So first will be at omega is equal to 0. K will be 1. So second sample will be at omega is equal to 2 pi by n. Then third sample will be at 4 pi by n. Then next will be at 6 pi by n, and so on. That means at interval of 2 pi by n, if the samples are taken of DTFT, we will get DFT and it is represented as xk. Now substituting the value of omega as 2 pi k upon n in the formula of DTFT, we will get DFT, which is summation xn e to the power minus j 2 pi kn upon n. But here the limit will be from n is equal to 0 to capital N minus 1, because now here xn is periodic in nature with the fundamental period of capital N. Now k will be having value 0 to capital N minus 1. Now we will define here twiddle factor Wn, which is given as e to the power minus j 2 pi by n. Now substituting twiddle factor, the formula for DFT will be given by summation xn wn kn, where n is from 0 to n minus 1. Now inverse DFT xn will be given by this formula 1 by n summation k is equal to 0 to n minus 1 xk e to the power j 2 pi kn upon n, where n is having value from 0 to capital N minus 1. Now if I compare DFT and DTFT, I'll say that continuous spectrum x omega of DTFT is replaced by discrete Fourier spectrum of DFT. Moreover, infinite summation in DTFT is replaced by finite summation in DFT. And the continuous frequency variable is replaced by finite number of frequencies located at 2 pi k upon nts, where ts is the sampling time. Because here DFT is obtained whenever we are doing sampling of DTFT. Now we will understand DFT by taking an example. If you want to find out DFT of unit impulse, we will use the formula of DFT. So here, instead of xn, we will put delta n. So here we will have delta n. I have already discussed that delta n is defined at only n is equal to 0, and it is having value 0 at other values of n. So we will take n is equal to 0. So delta 0, e to the power 0. E to the power is 0 is 1. Delta 0 is also 1. So DFT of delta n is 1. Here we can observe that DTFT and DFT of delta n is always 1. Whatever the transform we will take of unit impulse function, it is always unity. Now we will take another example. We will find n point DFT where capital N is 4 of sequence xn is equal to 1 between 0 to n minus 1. N minus 1 means 0 to 3. So we are having sequence which is having value 1 at n is equal to 0, 1, 2, 3. And it is having value 0 at other values of n. Now using the value of DFT, we will put n is equal to 0 to 3. Xn is having value 1, e to the power minus j 2 pi kn divided by 4. We will not consider another extended interval, because at any other values of n, the value of xn will be 0. So there is no need of writing summation in that range. Now, we know that k is having value from 0 to 3. That means from 0 to n minus 1. So first we will find the value at k is equal to 0. That means we will find x0. So when we'll put k is equal to 0, so it will be 1 into e to the power 0, which is 1. So expanding this summation, I'll get 1 plus 1 plus 1 plus 1, which is 4. Now next we will put k is equal to 1, which will be x sub 1. So in the formula, we will put k as 1. So we will get e to the power minus j 2 pi n upon 4. Now we will expand this summation by putting n is equal to 0, 1, 2, and 3. Now if I'll put n as 0, I'll get e to the power 0. If I'll put n1, e to the power minus j 2 pi by 4, then I'll put n is equal to 2 and n is equal to 3 and add all the terms. Now Using the Euler's formula, e to the power minus j 2 pi by 4 is given by cos 2 pi by 4 minus j sine 2 pi by 4. Similarly, for another term, then for third term also, I'll use Euler's term. Now, this is given as, if I'll solve it, it will be minus j. This value will be minus 1 and this value will be j. So after solving, I'll get x1 as 0. Now next I'll put k is equal to 2. So I'll get x2. Now in the formula, I'll put k as 2. I'll get summation e to the power minus j pi n. Now putting the values of n is equal to 0 to 3, I'll get e0 plus e to the power minus j pi plus e to the power minus j2 pi plus e to the power minus j3 pi. Now using the Euler's identity, I'll put e to the power minus j pi as cos pi minus j sine pi. Similarly, I'll use Euler's formula for second and third term also. After solving, here I'll get minus 1. For this, I'll get 1. And for this, I'll get minus 1. I'll get 0. So x2 is again 0. Now, I'll take k as 3 and I'll get x3. Now, putting k as 3, I'll get this expression e to the power minus j 6 pi n upon 4. Now, n will be taken from 0 to 3. Putting the values of n 0, 1, 2 and 3, I'll get this expression. Now I'll solve it by using Euler's formula. Instead of e to the power minus j 6 pi by 4, I'll write cos 6 pi by 4 minus j sine 6 pi by 4. Similarly, for this, I'll write this Euler's formula, and for this term, I'll use again Euler's formula. And here I'll get j. For this, I'll get minus 1. And for this, I'll get minus j. After solving, the value is 0. So k is having value from 0 to 3. That means xk will have x0, x1, x2 and x3. That means 4 values up there, which we have already calculated. Now writing it in the sequence form, xk will be 4, 0, 0, 0, because x0 was calculated 4, x1 was 0, x2 was 0, x3 was 0. So this will be my final sequence of DFT, which is 4, 0, 0, 0. Now this is how we can find DFT of any given finite sequence. Now this is all for today's lecture. Thank you.